Okay, so today we have Kevin Reardon from NSO. Kevin is expert on all things observational and also on the solar chromosphere. So yeah, today we will talk about image reconstruction in general. So we are basically continuing what we talked about during the last time. So we are talking about how to maybe get rid of some of these effects that we see that are polluting our observations. So without further ado, thank you, Kevin. Everybody enjoy and feel free to shoot any questions.
So yeah, the last week we went over the whole the convolution effect of the PSF and your optical system on the image that you get out, and how that the effects it has in Fourier space. So we had this example here where so you have in real space, you have a true object, your I0, right? That's what the sun looks like, that top image. And then it goes through your optical system, and because of diffraction effects and so on, you have this point spread function that's convolved with the image, and you end up with some observed image at the end. And then, of course, in the observed image there on the bottom, because you lose resolution and the effects it has in spreading out the light, the photons in different pixels, you get this smeared image. Now the nice thing is this convolution in real space is complicated, combining intensities from all the different pixels. The nice thing, of course, is in Fourier space, that's just a simple multiplication. So you can just take the image you observed, your true object, and the Fourier transform of the MTF. Look at those in Fourier space, and it's just a multiplication. So this seems pretty simple. It should just be entirely reversible, right? This is great. I can get my real image back, or the Fourier transform of my real image, that I can take back the real space by dividing my observed image by the MTF of my system, and so I'll get this. I'll get my true image back. So does this work? So here's an image on the left, is again, it's from a simulation, and the left is what you get with sort of the resolution of the simulation. So for a 4-meter diffraction limited image, and then I convolve that with the theoretical PSF of a 1.6-meter telescope, and you see slightly blurred out there on the right. So these bright points and everything are a little smeared out. So that's the effect of the convolution. But if I just take that image on the right, transform it back into Fourier space, divide it by the same theoretical MTF that I convolved it with in the first place, and then go back to real space, this is the deconvolved image now, and it looks very similar to that original input image. And so I've recovered almost all the information there through this simple deconvolution process. That's great. So what does this look like? Let's look at what happens with the MTF, and where does the MTF do the most damage when you're doing these convolutions? And so what does a typical MTF look like of a normal optical system? Well, just the effects of diffraction are sort of that green line. And so that's the effects of diffraction. And then, and so you see in that dotted green line that the attenuation, how it's reducing the power, is the amount of attenuation is increasing as you go to higher spatial frequencies, right? So it's dropping off steeply there. At the lowest frequency, it doesn't do anything. At the highest frequency, you get no power through, essentially. And there's a couple, the orange and the blue are a couple seeing BSFs. We'll get back to that later. And so, so we can look now. We'll take our image, that simulation image. We'll look at it in 1D for simplicity, just the radial power spectrum, radial average power spectrum. And so your image of that granulation has a lot of power at low frequencies, and then it tails off as we go to higher frequencies, up to the cutoff frequency for a 4-meter telescope up there at 102 arc seconds. So what does the MTF of that 1.6 meter telescope look like? Cuts off sharply there. Remember, this is in a log scale now, before we're looking at in a normal linear scale. And so that MTF drops off steeply at higher frequencies to the cutoff frequency there for a 1.6 meter telescope, which is significantly smaller than the 4 meter telescope, obviously. So that image that we looked at, the convolved image, has this power spectrum now. I've taken my input image, the red represented there by the red spectrum, convolved it with my 1.6 meter MTF, and I see that my power spectrum now of that image that the convolved image drops off steeply and falls well below the power of the input image. So that's why it appears blurrier. It doesn't have as much high frequency information in the image. So in my deconvolution, just divided basically that blue line by the green line, and now I have the power spectrum of that deconvolved image, and it just falls very nicely along the original power spectrum. So it's recovered everything. That's why that image looked so similar. It's recovered all that information. Now we've lost a lot of information at the very high frequencies there, past the cutoff frequency of that 1.6 meter telescope. Of course, that power is all very low. The amount of power out here past the 1.6 meter is comparatively low with respect to the power in the whole image, so we don't really notice that certainly by eye comparing the two images, because there's not a lot of power out there.
Can you repeat something?
Yeah.
I got confused with something.
Yeah.
So the red is the power spectrum of the actual intensity image, right? Over spatial scales.
Right.
The 1.6 green line is the MTF of the ideal telescope of 1.6 meters, correct? Mm-hmm. So the blue, light blue, I think, it's actually the multiplication of the two, correct?
Correct.
Correct. Correct. And then what do? You divide.
So then I just.
Oh, okay. Yeah. Awesome. So what you're saying is that yes, you do recover all your power, but up to a point, you kill all the highest, the spatial frequencies higher than a certain frequency. How do you define that? Is that what the need is?
Well, it's just where this MTF, so the MTF is, the scales over there on the right has fallen, it's a factor of 10,000 attenuation there, so it's just.
But so when you showed before the deconvolved image, your line, like the high frequencies are not there anymore. Oh, yes.
So this is the deconvolved image now.
Right, but I'm missing still.
So there is some, you have lost some high frequency power there. Okay. Right, and so you see that in Fourier space, when you see that you don't have some of the finest details in some of these structures.
Are still lost.
They're lost, right?
It's just that they don't come for much.
Right.
But where is what would be the uppermost possible limit? Shouldn't that be set by the sampling rate?
The sampling of
the sampling of your image here, right? Because still, if you don't have any diffraction, if you don't have anything, then the maximum frequency that you can see must be set by the sampling rate.
Right. So
then basically the right limit of the power spectrum of this is basically where it depends on
this red line here?
Yeah.
Yeah, so that the image was sampled such that the cutoff frequency equals, the sampling equals the Nyquist frequency of a 4 meter telescope. Okay. So yeah. So yeah, those are two, that's that spatial frequency there, the maximum spatial frequency.
Yeah. So in the previous image, you have your image array and you have a BSF array, and you Fourier transform them.
Yes.
And you divide them to deconvolve it.
Right.
Right. But in general, those two arrays won't be the same shape, right?
Right.
So
well, you would, yes. So you have to you have to make them the same shape, right? In the MTF. Normally, it's over a much smaller area, or in Fourier space, right, they both have to cover the same frequencies. Because I have a set of frequencies in my image here, right? And I need to divide all those frequencies, right? In some cases, it's all zeros. My MTF is essentially 0 at some of the higher frequencies. But I still need to, I mean, I could downsample image. Just here I maintained all the frequencies in the Fourier space, even in the convolved image, even though they were essentially 0. Right? I can just carry those.
I mean, one way to think about it is that this MTF in principle extends all the way to the right, but these are all zeros, and we don't want to delete by zeros, so we take all these zeros and we just shrink both our Fourier transformations of both the things to the limit where the MTF cuts off. So we basically by hand kill some frequencies in the original power spectrum or Fourier transformation of the image itself, so that we could do the division. It will be the homework.
The other way to think about it is this image on the right that I've convolved is now highly oversampled for a 1.6 meter telescope, right? It has 0.01 arc seconds, 0.013 arc seconds per pixel, which is well below the Nyquist sampling for a 1.6 meter telescope. So I could have rebinned that image down to the Nyquist sampling for a 1.6 meter telescope, right? And then I wouldn't have had those higher frequencies, you know, phantom higher frequencies in the Fourier space. Okay, so great, works great. Yay, we can deconvolve anything. Well, there's a couple problems, of course. So what we see here is that the MTF, right, of an optical system, right, most any optical system is going to, it drops off. I mean, this log scale, the power at high frequencies is being significantly reduced. That means when I do that division, my correction, right, is quite large. Here you see, you know, down here in this range, I'm already a factor of 10 correction I'm applying to my frequencies. So this is, you know, a big multiplication, and any errors there are going to be amplified. So why is that particularly problematic? Well, the big problem that we run into is our old nemesis, noise. Noise. So noise is a problem that we have to, and how we'll see how it affects our Fourier space here. And noise, of course, is present in any measurement. Here we're talking pretty, you know, about CCD detectors and images we're obtaining, you know, in the real world. And so there's two sort of key sort of noise components that end up in our data. One is just a read noise. So my detector, as it samples the amount of electrons or photons that it's collected, there's some error in that determination just from the electronics. That tends to be constant at all signal levels, right? So it's just a fixed offset, a fixed error in the electronics. So that's good. The other one is my shot noise, which is just an inherent property of a signal, especially, you know, I'm observing light from this ensemble of photons, and some of them are emitting and some of them aren't, and how many emit and send photons in my direction at any particular moment is just a statistical property, right? And so sometimes there's a few more, sometimes there's a few less photons emitted, and so that just depends on the square root of the total number of photons I'm detecting. So if I get fewer photons, I'll have my noise will be smaller, my shot noise will be smaller, but its proportion with respect to the signal will be higher. And if I go to collect more photons, that square root of the intensity will bring the relative noise down. And then the total noise that I see in my, you know, final image is just the quadratic sum of these two sources of uncorrelated noise. So one question is, so what are the units here, right? We're talking about the noise, and
So we don't have thermal noise.
so like there is a thermal noise, right? There could be a dark noise. That would be another, yes, just a statistical amount, you know. It'd be like the shot noise, you'd have a shot noise of your thermal background. The fixed part you can take out, right, in the dark current. That's, if the dark current is 100 and it was always 100, you can take that out. It's the, when it fluctuates, it's the fluctuations around that steady thermal component that it will get you.
Sure, but the dark noise is so much smaller.
The dark noise,
that
especially
when you add their noises, it's basically going to be the noise of the signal.
Right.
For the infrared though.
Well, in the infrared, yeah. In the infrared, with the corona, you know, where, you know, and spoiled in solar physics, normally our signals tend to be relatively high as we, you know, measure these weak coronal signals and things like that. We may have to go back to our infrared friends and learn about all the thermal issues and how to deal with that stuff. So yeah, the units of these things, right? You just have to be careful as you're calculating the units. You can do this either in actual photons, or sometimes it's easier to do it in DN, the data numbers, right? That's what comes out of your detector, and what's often written in your fixed file are these data numbers. And especially since the shot noise depends on the signal level, but not the signal level in DN, but the signal level in actual photons. In order to compute your, you know, total noise, figure out from your signal what the noise is, you just have to make that conversion from your DN intensity, the data numbers in your file, use the detector gain, the photons per DN, and convert that back into photons. So you're doing that quadratic sum in the same units. You know, that's the key part. Luckily, most of the detectors now, the readout noise is getting fairly small. But again, you know, infrared with coronal measurements and so on, it's, you know, still may be a problem. So how does these noise combine? So here, for plotted, assumed a 20 DN or 20 photon read noise. So that's the red line, just constant at all signal levels. And then for a variety of signal levels going from 1 photon per exposure, pretty low, up to 10,000. So that would give us a 1%, theoretically a 1% precision in our measurement. You know, how do those two noise sources combine, and what is our total noise? So at very low signal levels, the read noise dominates, and your total noise depends on the read noise. At very high signal levels, you know, it's up to 10,000. You're just looking at your all shot noise dominating. You really don't care about the read noise. And then there's this intermediate regime where both are contributing. And so, yeah, there's the part on the left is often called read noise dominated, and then on the right, it's the shot noise dominated. And it's important those two are, you know, that distinction there is important as you're planning observations. And you say, okay, I want to take some data, and I need a certain signal noise, and oftentimes you're going to have to combine multiple images and co-add some data in order to achieve that signal to noise. That co-adding, when you're summing up signals, is best done when you're in the shot noise dominated regime, because then you pay no penalty. If you're shot noise dominated, you can just co-add 2 signals, and the shot noise adds just as the signal adds, and you get the final noise is just the sum of the total signal. So you haven't added any other noise beyond what's inherent in your photon signal. If you're read noise dominated, you're adding signal, you're fighting a lot of read noise in your accumulation. So here is a plot saying, okay, I want to collect 10,000 photons, right? And I could either take a really long exposure and get 10,000 photons in a single image, and then I would have my 1% noise. My final relative noise would be down to 1%. That would be great, but maybe I need to take short exposures. Maybe I can't accumulate that long, And so maybe I have to take a lot of shorter exposures. Maybe if my signal level is just 100 per image, then I have to take 100 images to add it up. And so that blue line tells you in that, when you've co-added whatever number of images you need at that signal level, you'll get to the same number of photons. What is your final relative noise? And you see at low signal levels, if you're co-adding these images, you haven't reduced the noise to 1%, or as low down as if you had a lot of integrations or fewer integrations with a higher signal level. Sometimes you don't have the choice just because of different instrumental or observational effects. As we'll see, sometimes you want to take those short exposures in order to freeze the seeing and so on. So what your signal level is maybe, but you may not be freely able to choose that signal level.
So the 100 images, the green and the 1,000 is blue.
The green is the ideal.
Yeah.
10,000 would be, you'd have a 1% signal noise. They should all be, right? If you didn't have any read noise at all, they would all be 1%. If I had no read noise and I took 1,000 images with 10 photons, I would just have 10,000 photons and the same, it would all be shot noise.
Yeah. I was just saying the blue and the green are relative to 1,000 and 1. So there's no agenda on the blue.
This here with 10 counts, I'd have to take 1,000 images. If I had 10,000 photons per image, I would only need one image to get to my, to find my desired signal level. So what does noise look like? Well, noise. This is a nice image of noise in real space. You just have this random pattern. So what is this going to look like if I take a Fourier transform of noise? What do I get? There's a lot of high frequencies there, right? So you think, it's all going to be high frequencies. But if it was only high frequencies, you'd see a high frequency pattern, right? There would be some coherency and everything. So I don't see any coherence, any patterns across here, right? So, so when I transform this into Fourier space, I similarly get no pattern, right? There's no dominant frequency, there's nothing in there, it's just, again, this random distribution. So at all frequencies, I can take a slice or, so this was just random. I can look at this in 1D, and basically I just get my average power is the same at all frequencies for just a white noise. This is just a normally distributed white noise power spectrum. Some noise sources and detectors maybe have some structure to them, depending on the electronics or so on. But here, this is just for, say, photon shot noise, random distribution. We just have a nice flat power spectrum. And the value of that power, what that average value is, depends on what the value of the noise, of the average noise, the RMS of your input noise image. So, so how does that affect now our Fourier transform and our hope to be able to deconvolve everything? So again, I have the simulation there on the left, and now I have the same 1.6 meter image convolved with the PSF of the same image convolved with the PSF of 1.6 meter telescope, and now I've added 2% noise on that. I don't know if you can see that. A little bit. 2% noise isn't that much, right? The contrast, right? The RMS of the intensities in this image is 10 or 15% in this, certainly in these high resolution simulations, the values ranging plus or minus 40%. So 2% noise is, is hardly, not detectable, or it's hard to pick out visually. You're still dominated by the structures. But now what happens when I look at that image now, if I go back to Fourier space with that image, and what do I see? Well, so the red is again that simulation image. The blue was the convolved, that image convolved with the telescope with no noise. This orange line is if I just took the power spectrum of the noise that I was inputting there, right? And so that power spectrum is just that flat constant at all frequencies. And so when I combine these two, I now get this combined power spectrum where I've got the power spectrum now flattens out, now becomes dominated by the noise contribution of high frequencies. So instead of having just my input image, the original object multiplied by the MTF here, I now have this noise contribution that's added on there. So that's a problem because now if I try to deconvolve my image, I just divide that out by the MTF, there's that noise contribution that's going to get swept up in there. And so if I did this, so this is taking the image, deconvolve, that's what it looked like before, no noise, looks good. If I just do the straight deconvolution now without accounting for the noise, now I've amplified, right? I was multiplying those high frequencies by factors of 10 or more, and so now I've just blown up all the noise in my image. And so now it's become very noisy. So in practice, what you would like to do is you figure out the point where your image that becomes dominated by the noise, and you basically have to truncate your power spectrum there because you don't want to amplify that noise. You might hope you can, maybe there's some ways you can remove that noise, but even the noise measurement that realization of the noise in Fourier space is noisy in and of itself, and so you can't properly even just subtract off the noise in Fourier space any more than you could just subtract it out in real space. So you can apply a filter and you cut off frequencies, but then of course you're losing any possibility of correcting those frequencies from the MTF. So if I was to apply a filter and cut off the frequencies there above 10 per arc second because they become noise dominated, then I just wouldn't have those in my image. So the noise basically limits the resolution I can achieve in my final image. So a less noisy image is better, of course. That was 2% noise. Now I can reduce my noise by a factor of 10. Well, that's not too hard. I just have to integrate 100 times longer. Easy.
Easy peasy.
Easy peasy. So yeah, you can do that. There's prices to pay in your observational trade-off. But if I get to 0.2% noise, well, that's good. That's pretty low. Now that noise spectrum, that floor that I've run into, has come down, right? The total power of the noise is now reduced. And so where that flat part of the noise spectrum comes in, it's now a factor of 10 lower. So that's good. So now I have, I'm still seeing the power spectrum out, the actual solar part of the power spectrum out to higher frequencies. And now if I do the deconvolution, looks better. I haven't amplified the noise quite as much, but there's still some issues there. Now I'm getting some artifacts because of the effect of amplifying those high frequencies in the presence of some residual noise. You see ringing around the bright points. This is a classic problem when you're deconvolving a real image because you have this sort of sharp cutoff in Fourier space. And so now by truncating it with the MTF sharply there, when I bring it back to real space, I'm getting these effects of not being able to properly represent a true sharp cutoff in real space, and I get these ringing effects.
Why didn't you have them earlier when you had that much more noise?
I think in this other one here.
Yeah, the one with all, yes,
This
one.
I think they're there, but
they're just hidden.
they're just buried
Oh, okay.
below all the other noise that's been amplified at high frequencies. They're even there in the original image, the one without the noise. So the deconvolved, where was it? The deconvolved without the noise. If you actually take the difference of these two and look at them, you can actually see those artifacts are around all those bright points. You've got the effect of that sharp cutoff of the MTF truncating your frequencies, introducing some things there. So even when you're deconvolving an MTF, you have to be careful to smooth it out so you're not getting such a sharp transition between having power and not having power and everything going to zero to avoid those kind of artifacts. So there's a whole class of filtering that needs to be done. So it is possible to do this. You know, deconvolution is possible. We can get, you know, that was just a noise problem where we can integrate longer and take nice stable data where we know the PSF. So this is an example using Hinode. So that's a half-meter telescope in space. And so they calibrated the telescope before it went up, so they know exactly what the shape of the aperture is and how the obstruction, the centrally obstructed telescope. And so you can calculate a theoretical PSF of that telescope. But it turns out a theoretical PSF of some aperture is not nearly enough to do a good deconvolution. There's so much more going on in your optical system as you go through a variety of different optical elements that you know, the ideal calculation, ideal MTF or PSF is not enough. So in this case, they went, you can actually determine the PSF of a telescope by looking at stars. That would be great, but of course, solar telescopes tend not to be great at that. But if you look at any sharp object, right, you should be able to determine, and you know that the intensity should be, you know, something here and falls off to zero. It becomes possible to, you know, determine what the telescope PSF is from that. So the image there is an example looking at the transit of Venus. And so there you have this nice black cutout from your image that should be perfectly dark everywhere inside that black circle. And so you can look at the the radial trends across the disk of Venus, shown in the bottom there. And for your ideal MTF, you would have that black line, so it would be steep and drop off with a certain trend as you get further away from the planet or from the limb of the planet. But the gray lines show that it doesn't drop off always exactly as expected. You can also use the limb of the moon for this during partial eclipses. And so from that, you can go and try to determine a variety of parameters, do a series of fitting to get an MTF that properly fits the appearance of the limbs of these sharp objects. And you can determine these other additional contributions to the PSF. So the top one on there is the PSF, the log scale image and the log scale plot there. So that's the ideal PSF of the telescope. You see there's the central part, and then you see the effect of the central obstruction going out. So anybody know how many veins the central mirror of Hinode has?
Probably 3.
Yeah, so it's 3, so you see that. That's why it has the 6 diffraction spikes going out from that central obstruction and the supports for that. But then they did the whole scattered light computation, and they compute a series of parameters for a Lorentzian that then introduces scattered light from farther away than the simple PSF. They combine these all together and they get some optimal PSF to fit this. And so here, this is now an actual image. So the image on the left there is the granulation as observed. They just used the telescope PSF and deconvolved it. You get the central one. But if you use that fully derived PSF, including all the scattered light contributions, you see a much even more higher definition image there on the right. And so, from this, you can derive properties of the temperature fluctuations in the photosphere, match those to your simulations, and see if you're properly reproducing convective motions and the temperature changes they induce in the photosphere. So, it is possible. You need to be in space for that, generally, right? This was done with Node because they had this very stable BSF. So why do you need to be in space? Well, the ground-based BSF, that we have to deal with is far worse than just that simple telescope and optical system, because we're looking, as we talked about, we're looking through this atmosphere, and the dominant contribution to the PSF in our images is from the atmosphere. And so that PSF is rapidly varying as the atmosphere fluctuates. And so, we don't have a single well-known PSF for our image that we can apply to do a deconvolution. Now, one thing is we could average, we saw that if you have this long exposure, right, if you integrate these PSFs on average, if you accumulate enough or integrate for a long enough time, you get this average long-term PSF that should be more stable. So yeah, so I don't know what that is anymore, that MTF image. And it's varying over time now. Instead of just being this single MTF that I could apply this to, now I see my MTF from the ground is varying with time. It has this other dimension now in time. And so, but if I average over that, right, if I take the average and I average over time a series of realizations, I get this average PSF, which is the orange one. So the top is your nice seeing diffraction limited PSF in the absence of any seeing. And then if I look through the atmosphere and observe for a second or two, integrate, I get that seeing limited, much broader PSF, but it's stable. So this has been done by Jose, where you take a long exposure, basically, accumulating a lot of images. Your photon noise shot noise decreases, or the relative error, the error from your noise and this long exposure image is very small. And if I have the long exposure PSF, which you derive from the adaptive optics system that was running, you can then just do this deconvolution. And that's the image you see on the bottom there, where it's taken the long exposure image on the top, deconvolved it, and recovered some of those higher frequencies. This isn't great because you have to integrate for a long time, so you can't observe as quickly as possible. And also that long exposure PSF is really attenuating the high frequency, so it's making that problem of amplification of the high frequencies even more problematic. So,
when would that kind of exercise be useful? Never.
He did it. It hasn't been picked up on as a technique. Yeah. Yeah, I don't know. In some cases, in the coronal case, right? If you can't have AO anyway, or you don't have other ways to correct the image, or you can't take short enough exposures to freeze the seeing because you don't have significant signal, and the noise dominated part there, then maybe something like this might be.
But in that case, in this case, Jose used the AO data to derive the PSF, right? So the coronal would not.
So you wouldn't a priori know the PSF. So what do we do if we want to know the PSF? Good question. So how do we, if we don't know the PSF, how can we find it out? We have, this problem that PSF is varying in time, and we'd like to deconvolve it, but we don't know what it is. So we can take advantage of the fact that we can get multiple realizations, right? Because it's varying so quickly, we can take multiple images, right? And get multiple realizations of this combination of our object, which we assume to be fixed, or we observe quickly enough that our object, that is the part of the sun that we're observing, doesn't change, but the MTF is varying rapidly. And so I have a lot of images with different combinations of a fixed object and this time-varying MTF. That just sounds like some kind of solution, linear equation minimization problem to try to figure out some solution to that set of equations. So yeah, Ivan showed last week this, we have this, our PSF is really a combination of this A, our aperture, right? The shape of our aperture, whether that's has a central obstruction or not, just sort of a binary mask in intensity. And then a series of phases, which is the problem we get with the seeing, is it's introducing a series of phases across our pupil, and that's what's causing the distortions in our image beyond the simple optical diffraction. And so I'd like to figure out what those phases are, right? That's the key part. My aperture, the shape of my aperture shouldn't be changing in time. So I don't need to try to solve for the shape of my aperture. I'm trying to solve for the phases, the time varying phases. That's the part of the MTF that's changing. So what what can be done is you can take those phases, right? We saw this as just this sort of random distribution of phases due to the turbulent nature of the atmosphere, and I can try to. I want to solve this using a series of basis functions, right? Or some polynomials. I need to find a way to fit this and get an optimal fit, but I need to do that with some kind of polynomial, and so that's the basis function. And then the alpha is I just need to weight those different polynomials, and then I can get this map of the phases. So I want to solve for this vector of different weights for a fixed set of the basis functions. So the basis functions that we use typically are what are called, there's a variety of them. We want a series of functions that give us something that goes on our aperture, right? We're trying to find the phases, fit the phases typically across a circular aperture. And so I want a series of basis functions that work, that I can fit across a circular aperture. And so there's different ones of these. Classic ones are the Zerdeke polynomials. So these are a series of orthogonal polynomials in this circular space. And they break down, they go to higher degree. But there's the classical ones. You have the piston, so that's just a fixed constant offset. You have what's called the tip and tilt. So if I introduce phases, a phase gradient in one direction or another across my image, basically I'm changing the direction, the instant direction of my beam, right? And so that's going to cause my image in my focal plane to move, right? Make it appear like it's coming from somewhere else in the sky. And so tip and tilt will cause that shift. And then as you go to higher orders, there's that central one is defocus if you have some spherically symmetric phase shift, and then you get into all kinds of stigmatisms, and these go to higher orders with higher azimuthal frequency. Might be this is the same thing, but they're plotted in 3D, if that helps you. So yeah, so this is the tip tilt. Some of these with the shadow, those saddle shapes. Some of these exist optically as well. If you have an astigmatism, that's an effect of focus, this shift that across different directions in different part of the pupil that cause distortions in the image that can't be easily corrected. So I use this series of functions as my basis function, and I try to fit the series, the phases across my pupil with some number of these. And so there's that top there again. So I have this basis function. I have a series of alpha parameters. And we need to try to minimize and get the optimal fit here between, across all these this series of polynomials. And so one, function, Goodnessoffit function there, your L is comparing your actual observed image with the the complex conjugate of that image multiplied by your estimated MTF. So there's a little hat there. That's, you take a series of these polynomials, estimate an MTF, compare that, convolve it with the image, or multiply it with the image, and see if it matches your original image. And you do this over all the polynomials and all your different frequencies, and then you can sum up all those different fits. You can weight different frequencies in order to optimize that fit, and you can come up with some sort of best fit polynomial. So if you do this, it actually does work. So on the left there is the diffraction limited PSF. So you see nice diffraction limited PSF. And then for different values of that R0 that we talked about, the seeing, quality of seeing, you can recover to different degrees. So the top is the recovered, or the actual PSF, right, that you would get. This is through a simulation of the atmosphere, and you see the actual PSF through that atmosphere. And you see, as you get to worse seeing, you get a lot of structure in the PSF. When you fit that with these polynomials, you don't reproduce that perfectly. And so you get a much smoother PSF, but it does represent on large scale what the PSF of the image is. And on the bottom there is a series of masks, or a series of maps of, again, these simulated phase shifts across the pupil. So on the left column are the actual simulated phases from an atmospheric simulation. And in the right is what you recovered through some of these phase reconstruction techniques. So you can see, and depending on how many Zertiches you use there, on the top I think it's 25, and then 50, and then 100. Of course, you recover higher frequencies in your pupil, in the phases across your pupil, and you see there's some similarity to the original one. They're not, but it's not a perfect. You're not able to perfectly recover the pupil. It's also, of course, this problem is somewhat ill-posed. You have any number of combinations of pupils and so on, or phases that you could have, and so you have to treat this and put some constraints on the fitting of these polynomials to keep things from going below 0 and so on. So I think we'll stop there. Does anybody have any questions? Yes.
Yeah, I just wanted to see if I understood this properly, because I never thought about this. So basically what we do here is we have a series of images,
right,
where each original image is the same, but
right,
measured images are different because
right,
of the different state of the phase distortion.
Right.
But then we would like to fit for all the unknowns, which is phase distortion and the original image, knowing all these separate measured images,
right,
but it's too much to fit for all detailed phase distortions separately, so we just approximate them through various numbers of Zernike polynomials.
Right.
And then what we actually get as the output is the best fit for the original image and the best fit for the Zernike polynomials. So we have like some rough idea about the phase distortion, not with all the fine details, but right, just okay.
Yeah, and it's a fitting problem. There's tendencies for it to overcorrect at higher frequencies, and so there's issues. But it does give you that PSF out, right? You can calculate now. Like we did last week, you have this map of phases that you've fitted, and you can now create the PSF and get that inversion, or apply that deconvolution to get your image out.
So this is what's called the blind deconvolution.
So this is right. So this is called you have no. It's called a blind deconvolution because you don't really
a priori knowledge.
Limited number of a priori. You have your pupil, right?
Yes.
That's provided. But you don't have, you don't make assumptions about what the distribution of phases is across the people.
And this is fairly computationally expensive.
Right, because you're trying to go through and minimize, you know, all these different polynomials. And so yeah, there's a variety of numerical tricks to do that, but it's still a large system of equations. Yeah.
Would it help at all if you had like an external reference, kind of like we do for de-stretching? Like if you were doing this reconstruction in like the continuum, and you had a node A image of the same region. In principle, that gives you more information. It gives you some information about the
large scale.
Yeah.
You have to do the deconvolution of the node A image using all that.
Yeah.
But I guess it would. I suspect the large scale power is not the biggest issue.
Sure.
It's the high frequencies that you don't have. You can, we'll see next time, you can combine multiple, if those phase errors should be constant across your pupil no matter which wavelength you're looking at. They're not highly dependent, right? The atmosphere is causing the same phase errors, right, for all wavelengths, assuming they traverse mostly the same path of the atmosphere, which may or may not be true in diffraction, but you can use different images in different bands and help provide constraints here, because each one will have a realization of its own MTF, but based on the same set of phase errors. So since I'm really fitting the phase errors, I can use different wavelengths to try to determine what those phase errors are and correct that way.
One more question, but this may be, so basically we are limited how much we can deconvolve. We are limited by the cutoff frequency at our MTF, right? But what is super resolution then?
The super resolution?
Yeah. Like you always hear it, especially in these, you hear it a little bit in solar physics, but you especially hear it like in biotech. They talk about the super resolution, where you basically obtain the frequencies which are 2 times the Nyquist frequency.
Right. Yeah, I'm never sure how that works.
That sounds like fake news.
How they use it?
They use it routinely. It's just
Right.
I mean, you can see some serious people
No,
publishing papers about that, but it's just I'm always like interested how it actually works on paper.
Yeah, I don't know whether it's a similar solution of if you have the image, right? And if I have the same image and I move it slightly, right, I'm getting a different.
Yeah.
If I have a highly structured image and I move it slightly, and some of that intensity moves to a different pixel.
Sure. So you basically have sub-pixel resolution.
You might be able to recover, this was this small feature where it was located within a pixel, basically. Yeah.
Okay, that would be homework for me then.
So when you do this with the reference channel, that's in different wavelengths from your other channel, the PSF inside the instrument is different for the 2 channels, but the phases of the pupil of the telescope are the same.
Right.
So do you tell this to the codes we're using nowadays? Or?
So things like this, right? It can't. It's blind. It can't see anything that's constant between images. If I had a constant aberration in my telescope that wasn't captured in my circular PSF, it wouldn't know whether that was an aberration in the original, in the true object, or that was an aberration in your optical system because it's finding a constant thing and it's finding the time variant thing, separating those two. And so any constant aberrations are not, can't be determined through this. Though I don't know if you took, right, you have those phase masks. If I took my image now and I took a, right, I could build up those, I could accumulate those phase masks that this determines over time and start to, and if you see there's a constant phase error, I don't know if you'd see the constant.
It's gonna be a shit.
Yeah, you wouldn't even see the, it would just put it all in the object, yeah. Yeah, so yeah, these don't, constant things are not. Can't be determined. Okay, so yeah, so next week we'll see a different method to determine the BSF, and then we'll see how to apply these things to solar images. Oh yeah, Thursday. Thursday there might be some other similar images to look at.
Yeah.
Maybe.
Yeah, we'll definitely look at the things that are going to be published tomorrow. So
they're gonna put it out with a big draft in the middle. So so people want that.
It's already, yeah.
Somebody did say it.
You can use these techniques to remove the draft.
okay, so before we disperse, any questions from the people who are following online? Okay, well then, yeah, see you all
Thursday.
See you all Thursday. Yeah. Okay.
Merci.
Stop.
Stop.